Messerschmitt Me-262, the jet that arrived too late. The fastest fighter of the Second World War never won a single decisive battle. It could have. It was ready to fly combat missions in the spring of 1943. For more than a year after that, it sat on the ground, grounded not by enemy action, not by mechanical failure, but by an argument about whether it should carry bombs. The Me-262 was designed in 1938. Dr. Waldemar Voigt, working under Willy Messerschmitt at the company's design offices in Augsburg, began drafting the fuselage around a twin-engine jet layout that no one in any air force in the world had attempted before. The wings were swept back at 18.5 degrees, not for aerodynamic advantage at high speed, as engineers would later discover was possible, but simply because the engines turned out to be heavier than expected, and the center of gravity had shifted too far forward. The swept wing was an accident of engineering compromise. That accident would shape every combat aircraft built in the following 3 decades. The first prototype, designated V1, flew on the 18th of April, 1941, but it flew on a conventional piston engine fitted in the nose because the jet engines were not yet ready. The aircraft's first true all-jet flight did not occur until the 18th of July, 1942. Both BMW 003 turbojets failed during that flight. The pilot, Fritz Wendel, landed on the third engine, a conventional one that had been fitted as a safety measure. The next attempt used Junkers UMO 004 engines. That flight succeeded. By the spring of 1943, Wendel had pushed the prototype to 860 kilometers per hour, 534 miles per hour, and the aircraft was more than ready for service. Luftwaffe General Adolf Galland flew it and, in his own words, reported that it felt as though the angels were pushing him. He demanded it be deployed immediately as an interceptor against the American bomber formations that were destroying German industrial cities by day. The Army Air Force B-17 formations flew at roughly 450 kilometers per hour, 280 miles per hour, and carried defensive gunners but no fighter escort deep into Germany. The Me-262 would be faster than any of those bombers by more than 400 kilometers per hour, 250 miles per hour. At that speed differential, interception was not difficult. It was mechanical. Then Adolf Hitler watched a demonstration flight in November of 1943, and everything stopped. Hitler had been told by his armaments advisors that the aircraft could carry bombs. He decided that this was what the war required. Not a defender of German cities, but a fast attack aircraft, a blitz bomber, a lightning bomber, to strike Allied troop concentrations at the moment of invasion. He ordered the aircraft to be reconfigured accordingly. He called it the Blitz Bomber himself. When Galland attempted to explain that fitting bomb racks to a machine designed for speed and climb would negate its only real advantages, the conversation was ended. When Messerschmitt's engineers pointed out that the aircraft's undercarriage could barely absorb the stress of landing without bombs, they were also not listened to. The redesignated Me-262A-2A Sturmvogel, Stormbird, had fittings for two 250-kilogram bombs, each weighing 551 pounds, slung beneath its fuselage. The bomb racks added drag. The bomb aiming equipment added weight. Pilots assigned to drop bombs from an aircraft that flew at 870 kilometers per hour, 540 miles per hour. At low altitude, discovered that their aiming runs lasted approximately 4 seconds at that speed, and that hitting anything from such a pass was less a matter of precision than of probability. Most bombs missed. The Sturmvogel units recorded negligible effect on Allied positions. Meanwhile, the American 8th Air Force was sending formations of 300, 400, 500 bombers at a time over Germany. On the 14th of October 1943, Black Thursday as American air crews called it, 60 B-17s were shot down by conventional German fighters and anti-aircraft guns in a single raid on Schweinfurt. Had the Me-262 been available in numbers as an interceptor on that day, the outcome could have been substantially different. The ban on using the Me-262 as a fighter was only partially lifted in the late winter of 1944. The first true interceptor unit, Jagdgeschwader 7, became operational in the autumn of that year. The aircraft they flew was exceptional. Its 4 30mm Mk-108 cannons could break a B-17 apart with 3 to 4 hits. Its speed made it nearly impossible to intercept by conventional fighters. Pilots of the RAF and the USAAF learned quickly not to pursue an Me-262 in level flight. They also discovered its weakness. The Dumo 004 engines had a service life of barely 25 hours before they required complete overhaul. The alloys needed to build turbine blades capable of withstanding the heat of continuous jet combustion were in desperately short supply throughout Germany by 1944. Replacement blades were sometimes cast from inferior materials. Engines failed without warning. On more than one occasion, an Me-262 was destroyed not by enemy fire, but by an engine fire of its own making. The other weakness was the undercarriage. The jet exhausts created enormous heat, and the brakes on the main landing gear were prone to failure on landing. More critically, the aircraft accelerated slowly at low throttle settings, which meant that on takeoff and landing, it was briefly slower than conventional piston fighters. Allied commanders learned to position P-51 Mustangs and Spitfires over Me-262 airfields, waiting at altitude. When a jet came in low and slow to land, it was vulnerable for perhaps 90 seconds. Several were shot down in precisely this manner. 1,430 Me-262s were built between 1942 and 1945. Of those, perhaps 300 ever flew combat missions. The aircraft's kill-to-loss ratio was never precisely calculated, but estimates from Luftwaffe records suggest it shot down between 500 and 700 Allied aircraft. It was never enough. The production lines were bombed, the fuel was running out, the pilots were dying faster than the machines could be made. After Germany's surrender, every major Allied nation seized as many Me-262 airframes as could be found and reverse-engineered them. The Americans shipped examples to Wright Field in Ohio. The Soviets took aircraft and engineers. The British examined the engines and the swept wing geometry. Every jet fighter built in the world for the following decade descended in some way from the work done at Augsburg and Peenemünde. The aircraft that arrived too late for Germany arrived just in time for everyone else. STG-44, the gun that changed every gun that followed. Adolf Hitler banned its development. He ordered production to stop. He renamed it a machine pistol so that its existence would not appear in weapons development reports crossing his desk. And then, in the summer of 1944, When a general stood up during a briefing and shouted that what the troops desperately needed was more of these new rifles, Hitler looked genuinely confused. He asked, "What new rifle?" The general was referring to a weapon that had been in field testing for 2 years, under Hitler's theoretical prohibition, right in front of him. That weapon was the Sturmgewehr 44, which translates directly as storm rifle, model 1944. Before it existed, infantry combat in the Second World War was organized around a simple and brutal physics problem. Bolt-action rifles like the German Karabiner 98K and the American M1903 Springfield were accurate to 600 meters, nearly 660 yards, but slow to fire, requiring the soldier to manually cycle the bolt between every shot. Submachine guns like the German MP-40 and Soviet PPSH-41 fired rapidly on fully automatic, but were effective only to perhaps 100 meters, 110 yards, and fired pistol-caliber ammunition that lost its killing energy quickly. The two weapons occupied different tactical roles and could not substitute for each other. Hugo Schmeisser, who had already designed the MP-18, the first practical submachine gun in military history during the First World War, was given a development contract by the German Army in the early 1940s to solve this problem. He worked at the C.G. Henel Waffen- und Fahrradfabrik in Suhl. The solution he arrived at was elegant in its simplicity. Use an intermediate cartridge. The standard German rifle round, the 7.92 mm by 57 Mauser, was a powerful, full-length cartridge capable of long-range accuracy but producing heavy recoil when fired automatically. Schmeisser's design used a shorter, less powerful version of the same caliber, the 7.92 mm by 33 Kurz, Kurz meaning short. The Kurz round was effective to 300 meters, 330 yards, on full automatic, and to 600 meters, 660 yards, in semi-automatic fire. It split the difference between a rifle and a submachine gun. The weapon Schmeisser produced was designated the Maschinenkarabiner 42, H. It weighed 4.6 kilograms, 10 pounds, 2 ounces, unloaded. It fed from a 30-round detachable box magazine. It fired at approximately 500 rounds per minute on full automatic. When tested in field conditions on the Eastern Front, known in Russia as the Great Patriotic War, in 1942, the feedback from infantry soldiers was immediate and unambiguous. They could suppress Soviet soldiers armed with the PPSH-41 at ranges where the Soviet weapon was useless. They could still engage at rifle ranges in semi-automatic mode. The weapon worked. The problem was Hitler. He had issued a directive freezing development of new rifle designs. He believed the existing weapons in production should be maximized, not replaced. He had a logical concern. German industry was already strained to produce enough Karabiner 98K rifles for the Army, and introducing a new cartridge would require rebuilding every ammunition production line. These were reasonable objections, but the Army's weapons office had seen the results from the Eastern Front and did not want to stop. They did what bureaucracies do when an important project conflicts with executive authority. They disguised it. Schmeisser's Maschinenkarabiner was redesignated the Maschinenpistole 43. Machine Pistol, Model 1943, abbreviated MP-43. The name contained no word for rifle. Machine pistols were not on Hitler's list of frozen programs. Development continued. Small batches were distributed to frontline units. In 1944, a slightly refined version was approved, renamed MP-44. By July of 1944, it was in mass production. When Hitler finally was briefed on what his generals had been calling these new rifles, he was reportedly impressed enough to name it himself. Sturmgewehr, storm rifle, which gave the entire subsequent category of weapon, the assault rifle, its name. He ordered maximum production. 425,977 were eventually built between 1943 and April 1945. They were never produced in sufficient numbers to change the war's outcome. 425,000 rifles distributed across a German army of millions meant that most soldiers never held one. The Carabiner 98K remained the standard weapon. But what the STG-44 demonstrated, the concept, not the specific mechanism, was permanent. After the war, Hugo Schmeisser was taken by Soviet forces and transported to Izhevsk in 1946, where he remained until 1952. Those years overlap precisely with the period during which Mikhail Kalashnikov designed, tested, and finalized the AK-47. Kalashnikov disputed any direct contribution from Schmeisser. The historical record cannot settle the question. What the record does confirm is this. The AK-47 uses an intermediate cartridge, the 7.62 mm by 39, sitting in exactly the same performance envelope as the Kurz round. The AK-47's select fire mechanism, its detachable box magazine, its gas-operated action, every element of its tactical philosophy matches what Schmeisser built in Seoul. Today, the AK-47 and its variants are the most widely manufactured firearms in human history, with estimated production exceeding 100 million. The assault rifle is the standard infantry weapon of every army on Earth. Hugo Schmeisser died in 1953 in East Germany, 1 year after returning from the Soviet Union. He never held an AK-47. MG-42. When a machine gun rewrote infantry doctrine. When American soldiers first heard the MG-42 fire in Tunisia in 1943, they initially could not identify what they were hearing. The rate of fire, 1,200 rounds per minute, was so far beyond anything in their experience that the individual shots blurred together into a single, continuous, tearing sound. GIs called it Hitler's buzzsaw. The German manual called it Hämmerleins, little hammering. What it actually was a tactical revolution delivered through a sheet metal stamping press. The concept behind the MG-42 reached back to 1934, when the German Army had adopted the MG-34 as the world's first true general-purpose machine gun. The MG-34 was a superb weapon. It weighed 11 kilograms, 24.3 pounds, without its tripod. Fired the standard German 7.92 millimeter Mauser round at 800 rounds per minute, and could be reconfigured as a light infantry gun on a bipod, a heavy gun on a tripod, a vehicle-mounted weapon, or an anti-aircraft weapon, all from the same basic mechanism. It required 150 man-hours to manufacture. By 1941, German factories could not build them fast enough. The Metall- und Lackierwarenfabrik Johannes Grossfuss AG, a company based in Dobon that had previously made lamp fixtures and metal household goods, was given the contract to develop a replacement. The lead designer was Dr. Werner Gruner. The specification was direct. Produce a machine gun that performs at least as well as the MG-34, costs less, requires fewer man-hours to build, and uses more sheet metal stampings instead of expensive machine components. Gruner delivered a weapon that exceeded the specification in nearly every category. The MG-42 required 75 man-hours to manufacture, exactly half the time of the MG-34. Its unit cost dropped to 250 Reichsmarks from the MG-34's 327, and its rate of fire was not 800 rounds per minute. It was 1,200. Some specimens reached 1,500. The mechanism that produced this rate involved a roller-locked breech that cycled with extraordinary speed and a quick-change barrel that could be replaced in 6 to 8 seconds by a trained gunner wearing thick gloves. This was not a convenience feature. At 1,200 rounds per minute, a belt of 250 rounds, the standard combat load, was emptied in 12.5 seconds. The barrel would be glowing by the end of that burst. An overheated barrel that could not be changed meant the gun was out of action for several minutes while it cooled. The quick-change barrel meant a fresh one could be swapped and the gun was firing again in under 10 seconds. German machine gun teams typically carried 2 or 3 spare barrels on every engagement. The MG-42 was placed in action across all fronts by mid-1942. It immediately and fundamentally changed how Allied infantry had to move. The standard tactical doctrine in British and American infantry training was fire and movement. One section of soldiers fires to suppress the enemy while another section moves forward. Then the roles reverse. This works against a weapon with a cyclic rate in the hundreds of rounds per minute, where short bursts and brief pauses give the moving section moments of relative safety. Against the MG-42, with its continuous tearing fire, the calculation changed. A German MG-42 crew of 2 could suppress an avenue of advance that would require an entire platoon of bolt-action riflemen to cover. Allied infantry formations had to change their spacing, their speed of movement, and their reliance on smoke screens. Ernie Pyle, the American war correspondent who covered the Italian and French campaigns for American newspapers, described the sound of the MG-42 in a dispatch filed from Italy in 1943. It's like someone laying a stick along a metal fence and running it along the pickets. Except the pickets are bullets, and the fence is the field you're crossing. American training films produced in 1943 attempted to reassure GIs that the MG-42's bark was worse than its bite, that its high rate of fire wasted ammunition and reduced accuracy. The films were not entirely wrong about accuracy, but they understated the weapon's psychological effect and its suppressive power. In combat, an MG-42 that cannot be silenced can pin an entire company of men for hours. After Germany's surrender, the MG-42 did not end. West Germany rearmed in the 1950s and adopted a rechambered version of the same weapon, designated the MG3, in NATO's standard 7.62 mm caliber. The mechanism, the roller-locked breech, the quick-change barrel, all identical. The MG3 is still in production. It is currently used by the armed forces of 30 nations, including Germany. The weapon, designed in 1941 by a lamp fixture company, outlived the government that commissioned it by more than 80 years. V2, Vergeltungswaffe, the first missile that reached space. Shortly before 7 in the evening on the 8th of September 1944, a large explosion tore through Staveley Road in the Chiswick district of London. It killed a 63-year-old woman named Iris Mountney, a 3-year-old girl named Rosemary Clark, and a 28-year-old soldier home on leave from the Royal Engineers. The British government announced the cause as a faulty gas main. Nobody believed it. The sound of the explosion had no preceding warning, no aircraft engine noise, no air raid siren, no whistling fall. The blast simply arrived out of a clear evening sky from nothing. In the language of aerodynamics, the explanation was straightforward. The weapon had traveled faster than its own sound. By the time the explosion was heard, it had already happened. The weapon was the Aggregate 4, operational designation Vergeltungswaffe 2, Vengeance Weapon 2, contracted in Allied terminology to V2. It was the first ballistic missile ever used in warfare. It was also, by the strict definition of the term, a spacecraft. On the 3rd of October, 1942, during its first successful test firing at Peenemünde on the Baltic coast, the A4 prototype reached an altitude of 80 kilometers, 49.7 miles, which places it above the Kármán line, the internationally recognized boundary of outer space, by the definition used by the United States Air Force. Wernher von Braun had been interested in rockets since the age of 13. Born in Versitz, Germany in 1912, he joined the Verein für Raumschifffahrt, the Society for Space Travel, in 1928 while still in secondary school. He was less interested in warfare than in the stars. In late 1932, the German Army gave him a development contract for liquid fuel missiles, not because Army commanders had any particular strategic vision for rockets, but because the Treaty of Versailles had placed limits on conventional German artillery, and the Army wanted something beyond the treaty's language. Rockets were not explicitly prohibited. Von Braun saw in the military contract the funding he needed to build large rockets, and he took it. By 1937, he had moved his team of engineers and scientists to a purpose-built research facility at Peenemünde on the Baltic coast. The facility eventually employed a workforce of approximately 5,000 engineers, technicians, and scientists. It had wind tunnels, test stands, laboratories, a railway line, and by 1943, thousands of concentration camp prisoners from the Mittelbau-Dora camp system forced to perform construction and production work. At least 10,000 of those forced laborers died at Dora from starvation, beatings, or illness. The number of deaths at Dora exceeded the number of people killed by the V2 in combat. 3 early test firings in 1937 failed. A 4th failed. More attempts followed through 1940 and 41. On the 3rd of October 1942, a date von Braun himself later called one of the most important in the history of science, the A4 prototype rose from the Peenemünde launch pad and flew 190 kilometers, 118 miles, before impacting the Baltic Sea. Walter Dornberger, the Army officer commanding the program, told the assembled engineers afterward, "This 3rd day of October 1942 is the first of a new era in transportation, that of space travel." He was not wrong. He was simply describing a moment that had arrived on top of a weapon. The production V2 was 14 meters, 46 feet in length, and weighed approximately 13,000 kilograms, 29,000 pounds, fully fueled. It carried a 980 kilogram, 2,160 pound Amatol warhead. It burned a mixture of liquid oxygen and a 75% ethanol and water solution, consuming approximately 8,800 kilograms, 19,400 pounds of propellant in 65 seconds of powered flight. Peak velocity during ascent reached approximately 5,600 kilometers per hour, 3,478 miles per hour. At that velocity, no radar system, no anti-aircraft gun, and no interceptor aircraft then in existence could touch it. This was precisely the point. The V2 was Hitler's terror weapon, not merely in name, Vergeltungswaffe, vengeance, but in engineering specification. It could not be shot down. It could not be deflected. It arrived without warning and detonated below the speed of sound that preceded it. From the moment of launch in occupied Belgium or the Netherlands, fewer than 5 minutes elapsed before the warhead struck London or Antwerp. Between the 8th of September 1944 and the 27th of March 1945, 3,172 V-2s were launched operationally. Of those, 1,610 fell on Antwerp and 517 on London. The civilian death toll in London from V-2 strikes was approximately 2,724 people. A further 20,000 forced laborers died building the rockets at Dora. The strategic effect on the war's outcome was assessed after the armistice by Allied analysts as negligible. The V-2 was too inaccurate to destroy industrial targets. Its circular error probable was approximately 4 kilometers, meaning half of all rockets fell within a circle of 4 kilometers, roughly 2.5 miles, radius from the intended aim point, and the other half fell beyond it. Against cities, the weapon killed people. Against factories, railway junctions, or military installations, it was nearly useless. Werner von Braun understood this clearly. He understood it in the winter of 1945, when it became obvious that Germany would lose the war, and he made a decision that determined the next 25 years of human history. He arranged the surrender of 500 of his key engineers, the entire Peenemünde archive of 14 tons of technical documents, and a collection of rocket components to American forces in May of 1945. As part of Operation Paperclip, von Braun and 125 of his team were transported to Fort Bliss, Texas. He became a United States citizen in 1952. In 1960, he became director of NASA's Marshall Space Flight Center in Huntsville, Alabama. In July of 1969, the Saturn V rocket he designed launched 3 American astronauts toward the moon. The engine cluster of that rocket generated 34 million newtons of thrust at liftoff, the most powerful launch vehicle ever successfully flown. The A-4 had flown 80 kilometers. The Saturn V flew 384,000 kilometers. The U-boat snorkel, the device that turned a submersible into a submarine. Every U-boat that ever sailed in the Second World War was, technically speaking, not a submarine. It was a submersible, a surface vessel that happened to be capable of traveling briefly underwater. The distinction is not semantic. A true submarine can remain submerged indefinitely, or for as long as its air supply and crew endurance permit. A submersible must surface regularly, because its propulsion system requires contact with the atmosphere. The diesel engines that powered German U-boats on the surface could not operate underwater, where there was no oxygen to burn fuel. Submerged, U-boats ran on electric batteries. Those batteries discharged in hours and could only be recharged by the diesel engines. Every U-boat had to come up. Every time it surfaced, it could be seen. In the first 2 years of the Battle of the Atlantic, this limitation did not matter much. German Admiral Karl Donitz's Wolfpack tactics, coordinated attacks by multiple U-boats against Allied convoys, worked because the Allies lacked sufficient aircraft to cover the entire North Atlantic and lacked radar capable of detecting a surfaced U-boat at night. Between June and November of 1942, German U-boats sank over 400 Allied vessels. The tonnage lost, more than 2 million tons of shipping in 6 months, brought Britain measurably closer to starvation. Then 3 things happened at once. Allied long-range patrol aircraft equipped with centimetric radar could now detect a surfaced U-boat in darkness. The Allies cracked the German naval Enigma cipher with sufficient regularity to route convoys away from Wolfpack positions. And in May of 1943, 41 U-boats were sunk in a single month, including 8 in one day. Dönitz withdrew his submarines from the North Atlantic. The Battle of the Atlantic, as a German offensive strategy, was over. What followed was a German engineering crisis. The U-boat had been made into a weapon of precision, surface, and dive tactics. The Allies had turned the ocean's surface into a killing ground. The only answer was a device that had been sitting in German naval archives since before the war began. The schnorkel, from a Dutch word schnorkel, was a breathing tube. At its simplest, it was a pair of hollow masts that could be raised above the waterline while the submarine remained at periscope depth, roughly 12 to 15 meters below the surface, or between 39 and 49 feet. One mast brought air in for the diesel engines to burn. The other exhausted their combustion gases outward. A float valve at the top of the intake mast sealed automatically if waves broke over it, preventing seawater from flooding the tube. When the valve closed, the diesel engines briefly sucked air from inside the pressure hull, a process that crews described as a rapid, painful drop in air pressure, comparable to having one's ears squeezed from outside. Then the valve opened again, and the cycle resumed. It was crude. It was uncomfortable. The snorkeling U-boat's acoustic sensors were largely useless. The noise of its own engines drowned out any incoming sound. It could not use its radio effectively at shallow depth. The diesel exhaust occasionally trailed a visible plume on the water's surface. Allied radar, in theory, could still detect the small radar cross-section of a raised snorkel mast. In practice, detecting a mast of 40-centimeter diameter, approximately 16 inches, at speed across the North Atlantic in variable sea states proved far more difficult than detecting a surfaced submarine. The first production snorkel-equipped U-boats entered service in the summer of 1944. Their tactical effect was immediate. U-boats returned to the British coast, where they had been driven away by Allied patrols, and sank vessels in waters that had been considered safe since 1943. More importantly, the snorkel extended the endurance of a submerged U-boat from a matter of hours to a matter of days. A crew could remain submerged for a week or more, surfacing only briefly at night to fully recharge batteries, and then dropping back below. Anti-submarine patrols that had been methodically destroying surfaced U-boats found themselves hunting ghosts. The snorkel's ultimate expression was the Type 21 submarine, the first vessel ever designed from the keel upward as a true submarine rather than a submersible. The Type 21 was 76 meters, approximately 249 feet in length, and displaced 1,621 tons surfaced. Its battery capacity was triple that of previous U-boats, giving it an underwater endurance of several days between snorkeling sessions. Its underwater speed on battery power reached 17 knots, roughly 31 kilometers per hour, faster than most Allied escort vessels. It carried hydraulically powered torpedo tubes that could reload in 12 minutes without crew labor, compared to the 20 minutes of exhausting manual effort required in older boats. It was equipped with advanced sonar, a snorkel as standard, and rubber acoustic dampening coatings on parts of its hull. Had the Type 21 entered service in numbers by the spring of 1944, when the Allied invasion of France was still months away and the Atlantic supply lines were critical, the consequences for the Normandy campaign are difficult to calculate. The invasion of France required the delivery of millions of tons of men, fuel, ammunition, vehicles, and food across the English Channel and the Atlantic. A submarine that could not be reliably located traveled faster submerged than the escorts were designed to catch, and reloaded torpedoes mechanically would have imposed casualties on that supply chain that no Allied planner had modeled. It did not happen. Allied bombing of German shipyards destroyed or delayed more than half the Type 21 production run. only two Type 21s, U-2511 and U-3008, became operational before Germany's surrender. U-2511 was at sea when the armistice was announced. Her commander, Kapitänleutnant Adalbert Schnee, recorded in his war log that he had tracked and gained firing position on the British cruiser HMS Norfolk, undetected, before receiving orders to cease hostilities. He did not fire. He surfaced and returned to port. After the war, every major naval power studied the Type 21 and the Schnorkel in detail. The United States Navy's Greater Underwater Propulsion Power program, the Guppy conversions, retrofitted existing American submarines with enlarged battery banks, streamlined hulls, and Schnorkel systems directly modeled on German designs. The Soviet Union built submarines in the 1950s based heavily on Type 21 specifications captured from German yards. The Schnorkel is installed on every conventionally powered submarine in service anywhere in the world today. A device tested in 1943 and deployed in 1944 became a permanent feature of underwater warfare for the remainder of the 20th century and well into the 21st. Hankel H-178, the 6-minute flight that ended the piston age. On the 27th of August, 1939, an aircraft flew over Rostock-Marienhalle airfield in northern Germany for 6 minutes and returned to the runway. Nothing about it was remarkable to look at. A compact metal fuselage, high-mounted wooden wings, a fixed undercarriage. The pilot, Flugkapitän Erich Warsitz, described the takeoff as routine. The landing was uneventful. Ernst Haeckel, watching from the grass beside the runway, shook Warsitz's hand. 3 men had lunch together. Then they went back to work. 4 days earlier, on the 23rd of August, the Molotov-Ribbentrop Pact had been signed in Moscow. 9 days after the flight, Germany invaded Poland. In the cascade of events that opened the most destructive war in human history, the 6-minute hop over a German airfield was not noted by any newspaper, any radio station, or any government outside the company that had built the machine. But what Erich Warsitz had done that morning had never been done before in the history of human flight. The HE-178 was the first aircraft in the world to fly using only the thrust of a turbojet engine. The piston era, 36 years old, from Kitty Hawk to Marienhalle, was over. Hans Joachim Pabst von Ohain was 25 years old when he filed a patent in 1935 at the University of Göttingen for a method of using the exhaust of a gas turbine as the primary propulsive force for an aircraft. The concept was not entirely original. The British engineer Frank Whittle had filed a remarkably similar patent in 1930. Whittle and von Ohain arrived at essentially the same idea independently, within 5 years of each other, working in separate countries with no knowledge of each other's work. Von Ohain's patent was filed. His government was not interested. He took his drawings to Ernst Haeckel in the spring of 1936. Haeckel was a man of a particular type, an aircraft manufacturer who was genuinely excited about aircraft. He was not interested in the HE-178 as a weapon. He was interested in it as a proof of concept, a demonstration that the gas turbine could replace the piston engine in flight. He funded the development privately, as a company venture, independent of the Luftwaffe and the Reich Air Ministry. The first engine, designated HES-1, burned hydrogen as fuel, produced 250 kilograms, 551 pounds, of thrust, and ran on the test bench in September of 1937. It was too weak to fly anything. Von O'Hain designed a second engine and a third. The HES-3B ran on petrol, produced 490 kilograms, 1,080 pounds of thrust, and was installed in the HE-178 airframe in the summer of 1939. The first unpowered glide tests of the airframe were conducted with a tow aircraft. The first powered hop, wheels briefly leaving the ground, occurred on the 24th of August, 1939. 3 days later, Warsitz made the full flight. He managed 2 circuits of the airfield before a bird was ingested by the engine intake, causing a partial loss of thrust. He brought the aircraft back and landed. The engine was examined. No serious damage. The flight was declared a success. Heinkel wrote to the Reich Air Ministry and requested a formal demonstration for Luftwaffe officials. The ministry replied that it was somewhat busy. It was September of 1939, and German forces were engaged in Poland. It was not until the 1st of November 1939 that Air Ministry representatives Ernst Udet and Erhard Much were finally flown to see the HE-178. Both men came, watched Warsitz take off, fly 1 circuit, and land. Both men were not impressed. Udet noted that the aircraft's top speed, 598 kilometers per hour, 371 miles per hour, was comparable to existing piston fighters already in service. He pointed out that the HES-3B engine consumed fuel at a rate that gave the aircraft an endurance of only 10 minutes. Milch agreed. Neither man requested further development. The HE-178 was placed on static display in the Deutsches Technikmuseum in Berlin. In 1943, an Allied bombing raid destroyed the museum. The original airframe was lost. Heinkel continued development regardless. He built the HE-280, a twin-engine jet fighter, which flew on the 2nd of April, 1941, the world's first jet-powered fighter, which the Luftwaffe also declined to develop. He built the HE-162 Volksjäger, People's Fighter, a single-engine jet designed to be flown by minimally trained pilots using non-strategic materials, which entered service in the final months of the war. He designed engines that found their way through various channels into the Messerschmitt Me-262. The 6-minute flight over Marienhalle in August of 1939 made all of it possible. Frank Whittle's Gloucester E.28/39, the British jet prototype, did not fly until the 15th of May, 1941, 20 months after the HE-178. The Americans did not fly a jet aircraft until the 2nd of October, 1942. By the time the United States, Great Britain, and the Soviet Union were flying jet prototypes, Germany had already been operating a jet engine in the air for 3 years. That lead was squandered, meeting by meeting, from November of 1939 onward, in a series of offices where men who could not imagine what they were looking at chose to look away. Panzer V, Panther, the tank that was its own worst enemy. On the 5th of July, 1943, 200 Panther tanks rolled toward the Soviet defensive lines at Kursk. By the evening of the 6th of July, 40 were still operational. By the evening of the 7th, 10. In 2 days of fighting, 190 Panthers had been lost. Not to Soviet guns, not to Soviet tanks, not to mines or artillery. The majority had stopped moving because they had broken down. Their engines overheated, their transmissions seized, their final drive housings cracked under load. In the field south of Kursk, on what was supposed to be the decisive offensive that would restore German momentum on the Eastern Front, known in Russia as the Great Patriotic War, The most advanced tank Germany had ever built destroyed itself. The Panther's origin was a tank the Germans had not built. When Germany invaded the Soviet Union in June of 1941, Operation Barbarossa, German tank crews encountered two Soviet vehicles that their existing armor could not reliably defeat: the KV-1 heavy tank and the T-34 medium tank. The T-34 was not heavier than German tanks. It was cleverer. Its armor was sloped, angled at 60 degrees from vertical on the front hull, which meant that an incoming shell, rather than striking flat metal perpendicularly, struck at an angle. The geometry of the impact lengthened the effective path through the metal and also increased the probability that the shell would deflect entirely rather than penetrate. The actual plate thickness on the T-34's blaces was only 45 millimeters, 1.77 inches, but the slope made it resist penetration equivalent to approximately 90 millimeters, 3.54 inches of vertical plate. German anti-tank guns that could punch through the armor on a Panzer III or Panzer IV at ranges of 500 meters, 547 yards, were struggling to kill T-34s at 200 meters, 219 yards. The German Army responded in November of 1941 by commissioning a new tank. The specification issued to Daimler-Benz and MAN, Maschinenfabrik Augsburg-Nürnberg, demanded sloped armor, a powerful long-barreled gun capable of defeating Soviet armor at range, and a weight limit of 35 metric tons, 38.6 short tons. Daimler-Benz submitted a design so directly modeled on the T-34 that it was, in the view of several Army officials, essentially a licensed copy. The same wide tracks, the same hull shape, the same diesel engine, the same turret placement. MAN submitted a more conventional German design, but incorporated the critical lesson of slope. MAN's design was selected. Hitler was reportedly displeased. He had preferred the Daimler-Benz version, but the decision stood. Production of the Panther Ausf D began in January of 1943. The weight had already grown from the specified 35 tons to 44 metric tons, 48.5 short tons, by the time the first vehicles left the factory at MAN's plant in Nuremberg. The glacis plate was 80 millimeters thick, 3.15 inches, sloped at 55 degrees from vertical. The effective protection it provided was calculated at approximately 140 millimeters, 5.5 inches, of vertical plate equivalent. No Allied tank gun in service in 1943 could reliably penetrate it from the front at combat ranges. The main gun, a 7.5 centimeter KWK-42 with a barrel length of 70 calibers, could penetrate 140 millimeters, 5.5 inches, of vertical plate at 1,000 meters, 1,094 yards, and 111 millimeters, 4.37 inches, at 2,000 meters, 2,187 yards. At the ranges that German tank doctrine preferred, the Panther could kill any tank then in Soviet service before the Soviet crew knew it was under fire. It could not, however, drive to the battle without breaking down. General Heinz Guderian, the Army's Inspector General of Armored Troops and the man who had pioneered German tank tactics in France in 1940, visited the Panther production lines in June of 1943 and came away alarmed. He wrote in his report that 45 mechanical defects had been identified in the drive chain, transmission, motor, and fuel pump systems, and that many of these defects caused the engine to catch fire. He requested that the Panther's commitment to the upcoming Kursk offensive be postponed until the faults were corrected. Hitler refused. Kursk, planned as Operation Citadel, was already delayed, and the Panther was supposed to be its decisive technological factor. Of the 200 Panthers deployed to the Gross Deutschland Panzer Grenadier Division and Panzer Regiment 39, 16 broke down during the rail transport to the front before the battle even began. On the first day of fighting, the 5th of July, the Panthers' inexperienced crews encountered Soviet defensive lines that had been prepared for over 2 months, based on intelligence about the German offensive obtained through the British Ultra Intercept program. Soviet engineers had laid an average of approximately 5,000 anti-tank mines per kilometer, 1,600 feet of front. Panthers began hitting mines immediately. Others stopped with overheated engines or failed transmissions. Fuel pump failures caused engines to catch fire. By late afternoon of the 5th, the figure of 200 operational Panthers had collapsed toward a number that no senior German officer in the Panthers' command chain could accurately determine, because so many vehicles were spread across fields at various stages of mechanical failure. The combat that followed over the next 5 days was not without Panther successes. At ranges of 1,000 to 2,000 meters, 1,100 to 2,187 yards, Panthers destroyed T-34s reliably. Their frontal armor survived hits from Soviet 76mm anti-tank guns that would have penetrated any previous German medium tank. In the records of engagements during Kursk, individual Panthers are documented destroying multiple Soviet tanks in single actions. The problem was that too few were working at any given moment. By the 10th of July, 10 Panthers faced the enemy. 25 were total losses. 100 were in repair shops. 44 of those had been put there by mechanical failure alone, with no combat damage whatsoever. One Panther, disoriented in the fighting, was misidentified as a Soviet vehicle and was destroyed by a German Panzer IV. Its crew could not escape in time. The defects were progressively corrected through the autumn and winter of 1943. The Panther Aus A, entering production in September of that year, addressed the most serious transmission and engine problems. The Aus-G, produced from the spring of 1944, was a substantially more reliable vehicle. 6,000 Panthers in total were produced across all variants. In Normandy, in Italy, and on the Eastern Front through 1944 and 1945, the corrected Panther was regarded by tank commanders on both sides as the finest medium tank of the war. Its sloped armor geometry, its gun, its balance of protection and firepower became the template. The American M48, the Soviet T-54, and virtually every main battle tank designed in the decade after the war incorporated angled glacis plates derived directly from what the Panther had demonstrated, and what the T-34 had demonstrated before it. Every main battle tank currently in service in any army on Earth, without exception, uses sloped armor. The Panther's most lasting contribution to armored warfare was the lesson it failed to teach quickly enough to save itself. Henschel HS-293, the missile that invented modern war. Every anti-ship missile fired in every naval conflict since 1945, every Exocet, every Harpoon, every Silkworm, descends conceptually from a weapon that most people have never heard of. It weighed 1,045 kilograms, 2,304 pounds. It had a wingspan of 3.1 meters, just over 10 feet. A small rocket motor in a pod beneath its body burned for 10 seconds, accelerating it to approximately 260 meters per second, 850 feet per second, and then cut out, leaving the weapon to glide on its wings toward the target, while a bombardier in the launch aircraft watched it through a Kell Strasberg radio control unit and moved a joystick to steer it. The magnesium flare in the weapon's tail burned brightly, so the bombardier could track it visually against the dark sea below. When he judged the approach correct, he let it go. Dr. Herbert Alois Wagner joined the Henschel Flugzeugwerke in the spring of 1940 and was given the task of converting a pre-existing unpowered glide bomb project into something guided and propelled. Wagner was a physicist with a background in aeronautics, and he understood from the beginning that the fundamental problem with attacking a defended warship from an aircraft was not a problem of explosives. It was a problem of range. An aircraft approaching close enough to aim a conventional bomb was already inside the defensive anti-aircraft envelope of every armed vessel larger than a destroyer. At 3,000 meters altitude, 9,843 feet, a bomber was within range of dozens of automatic weapons. Below that, the problem became worse. The solution was a weapon that could be aimed and released from outside the anti-aircraft envelope and then guided to the target from a distance. The first flight test of the HS-293 was on the 16th of December, 1940. The left and right control circuits had been accidentally reversed during assembly. The weapon turned the wrong way and was lost. Subsequent tests corrected the wiring and progressively refined the guidance system. By 1942, the weapon was in limited production. On the 25th of August, 1943, 12 Dornier Do-217 bombers of the second group of Kampfgeschwader 100 attacked British anti-submarine forces in the Bay of Biscay. One HS-293 hit the British sloop HMS Bidford. The damage was insufficient to sink it. 2 days later, on the 27th of August, the same unit attacked a convoy escort group. This time the results were unambiguous. HMS Egret, a sloop of 1,100 tons, was struck and sank within minutes. It was the first warship in history to be sunk by a guided missile. Between August of 1943 and the end of the year, HS-293 attacks sank or seriously damaged more than 24 Allied vessels. The British destroyer HMS Inglefield went down. HMS Dulverton was sunk. The Greek destroyer Vasilisa Olga was destroyed. In September of 1943, as Allied forces landed at Salerno in southern Italy in Operation Avalanche, HS-293 equipped aircraft attacked the crowded anchorage of landing ships and transports. The hospital ship HMHS Newfoundland was struck, despite its clear Red Cross markings, and caught fire. The British troop ship Santa Elena was set ablaze with American soldiers aboard. But the weapon's most devastating and least remembered strike occurred on the 26th of January, 1944, in the waters off the Anzio beachhead in Italy. The American troop ship SS Roosevelt was struck and sank. But the more catastrophic blow came when HS-293s found the landing ship LST-348. The precise chain of events resulted in casualties among American soldiers still aboard the vessel. The United States government classified the full record of casualties from HS-293 attacks in the Mediterranean for reasons of morale and operational security. Some accounts of the combined Anzio losses from guided bomb attacks cite over 1,000 American soldiers killed in a concentrated period of days, a figure that remained absent from public accounting for decades. The HS-293's vulnerability was the radio link between the bombardier and the weapon. Allied signals intelligence quickly identified the frequencies used by the Kell-Strasberg guidance system. By late 1943, British destroyers and escort vessels were equipped with jamming transmitters set to broadcast noise on the guidance frequencies. A jammed HS-293 flew straight and level until it hit the water. The Germans attempted to shift frequencies, introduce new guidance codes, and eventually develop wire guidance variants that could not be jammed through radio. None of these solutions came quickly enough. By 1944, the Allies' air superiority over the Atlantic and Mediterranean had also made it increasingly difficult to position launch aircraft at the altitudes and distances required for effective HS-293 attacks. The weapon remained in use through the end of the war, but its window of effectiveness, perhaps 12 months from August of 1943 to the summer of 1944, had closed. Approximately 1,200 HS-293s were produced. Henschel became the first company in history to mass-produce guided missiles. The production of the weapon's precision airfoils was assisted by a pioneering digital computing device developed by Konrad Zuse, one of the earliest practical uses of digital computation in industrial manufacturing. The Argentinian Navy used French-supplied Exocet anti-ship missiles to sink HMS Sheffield and the Atlantic Conveyor during the Falklands War in 1982. The Exocet works on the same conceptual principle as the HS-293. Launch from outside the defensive envelope, guide to the target, strike the hull at or near the waterline. The specific mechanism, sea skimming, active radar homing rather than visual guidance, is more sophisticated. The concept is the same. It was Wagner's concept. It was Henschel's production line. It was the 27th of August, 1943, in the Bay of Biscay, when the first guided missile in history sank the first ship ever destroyed by one. T-5 Zaunkönig, the torpedo that chased propellers, including its own. In December of 1943, the German submarine U-972 disappeared in the North Atlantic. No wreckage was found. No distress signal was received. No Allied anti-submarine patrol reported a contact in the area where the U-boat was last known to operate. The cause of the sinking was never officially confirmed. The most probable explanation, reconstructed from the operational records of similar incidents, is that U-972 was sunk by one of her own torpedoes. The weapon in question was the G-7E's Zaunkönig, Wren in German, designated T-5 by the German Navy and codenamed GNAT by British Naval Intelligence. GNAT stood for German Navy Acoustic Torpedo. It was the first operational acoustic homing torpedo in history, a weapon that did not require a human to aim it at a specific target because it found the target by itself. The guidance mechanism was two hydrophone receivers mounted in the weapon's nose, tuned to detect the cavitation frequencies of ship propellers, the broadband noise created by spinning blades churning water. When the T-5 sensed that the sound was louder on the left than the right, it turned left. When it was louder on the right, it turned right. It flew, blind and mechanical, toward the loudest propeller noise it could detect. The problem was identifying whose propeller it was hearing. Development of the T-5 traced back to the late 1930s when engineers at Atlas Werk in Bremen began work on a passive acoustic seeker head adaptable to standard German torpedo dimensions. All German submarine torpedoes were 53.3 centimeters, 21 inches, in diameter and could be loaded in standard bow tubes without modification. The first practical acoustic torpedo, the T-4 Falcon, entered service in March of 1943 and was used by 3 U-boats against convoys HX-229 and SC-122 before being superseded by the faster and more capable T-5. The first 80 T-5s were delivered to U-Boat Command on the 1st of August 1943. The weapon was ready for mass operational use by September. The T-5's operating parameters were carefully defined. It ran straight for 400 meters, 437 yards, from its launch point before the acoustic seeker activated. This straight run delay was a safety measure. A torpedo that began homing immediately after launch would hear the submarine that fired it, because the submarine's own propellers, turning its speed for the attack approach, were the loudest sound source in the water. The 400-meter run gave the U-boat time to clear the weapon's search cone before the seeker turned on. The standard tactical order after firing a T-5 was to dive immediately to 60 meters, 197 feet, below the surface and shut down all machinery. Silence. No propeller noise. The theory was sound. The mathematics were correct. And then U-972 went missing, and in January of 1944, U-377 disappeared in similar circumstances. No certain explanation for either loss survives in the documentary record. What U-Boat Command's operational analysts concluded was that in both cases, the most likely scenario was a shorter than normal transit run before the seeker activated, perhaps caused by a calibration error or a manufacturing defect in the acoustic unit, allowing the torpedo to hear the launching submarine before the boat had reached 60 meters depth and stopped its engines. A T-5 running on full power at 24 knots, 44 kilometers per hour, 27 miles per hour, with an effective range of 5,700 meters, 3.5 miles, could circle back and close the distance to a submarine trying to dive in under 2 minutes. Standing orders after the loss of U-972 were amended. Dive faster. Go silent sooner. The weapon's first large-scale combat use against convoy ON-202 in the North Atlantic from the 20th to the 24th of September 1943 produced results that were initially reported as exceptional. U-boat commanders logged multiple torpedo strikes and submitted claims of 9 merchant steamers and 12 escort ships sunk. The actual tally, confirmed by Allied records, was 6 merchant ships and 3 escorts, 1 destroyer, 1 frigate, and 1 corvette. The T-5's acoustic steering, while revolutionary in concept, was imprecise. The seeker tended to fixate on the loudest sound rather than the closest target, and propeller noise behind a ship, in the churned wake, was often louder than the noise directly beneath the hull. A significant number of T-5s detonated in ships' wakes, destroying nothing but water. The Allied response was the Foxer, British designation, and the FXR, American designation. Both were acoustic decoys, noise-making devices towed several hundred meters behind an escort vessel on a long cable. The devices mechanically generated broadband noise at frequencies that overlapped with propeller cavitation, far louder in the T-5's hydrophones than the ship's actual screws. A convoy escort towing a Foxer essentially extended a decoy louder than itself behind its stern. The T-5, homing on the loudest propeller noise, flew toward the Foxer. It missed the ship and hit nothing, or detonated at the end of its run in empty water. The Foxer was deployed on all transatlantic escort vessels by late September of 1943. The same month, the T-5 made its operational debut. The weapon and its counter arrived in service almost simultaneously. German engineers modified the T-5's seeker frequency in an attempt to defeat the Foxer. The modification helped partially. Allied decoy designs were adjusted in response. The cycle of measure and countermeasure that defines every subsequent guided weapon development began in the North Atlantic in the autumn of 1943, between a torpedo that could hear and a decoy that could shout louder. 640 T-5 Zornkönig torpedoes were expended in operational use through the end of the war. They sank or damaged enough escort vessels to confirm the concept, and enough friendly submarines to confirm the hazard. Every passive acoustic homing torpedo built by any Navy in the 60 years that followed used the same fundamental mechanism: hydrophone receivers in the nose, electro-pneumatic steering, a seeker that hunts sound. 2 submarines were almost certainly destroyed by their own inventions. They remain, officially, missing. Focke-Wulf FW-190, the fighter that no one was prepared for. In September of 1941, RAF Fighter Command's intelligence officers received a report from a combat pilot that they initially refused to believe. The pilot, from 71 Eagle Squadron, composed largely of American volunteers flying Spitfire Vs over the English Channel, described being attacked by a radial-engine German fighter he did not recognize. The aircraft had outrun his Spitfire in level flight, outclimbed it, and outrolled it. He had not been shot down, having broken contact in a dive. When he returned to base and described the encounter, the intelligence section told him he must have engaged a Curtiss Hawk, an American export fighter sold to France before the fall of Paris, and captured by the Germans in large numbers. Radial engine fighters in the Luftwaffe were either captured equipment or training aircraft. The Messerschmitt Bf 109, with its inline engine, was the German standard. The intelligence section was completely wrong. What the pilot had encountered was the Focke-Wulf FW-190A, which had been flying combat missions over France and the Channel since September of 1941. The aircraft had been in development since 1937, designed by Kurt Tank at Focke-Wulf Flugzeugbau in Bremen. Tank had begun with a simple conviction that the radial air-cooled engine, dismissed by most European aircraft designers as too bulky and drag-producing for a high-performance fighter, could be tamed with a sufficiently well-designed cowling. The BMW 801 engine he selected produced 1,560 horsepower, eventually raised to 1,700 horsepower in later variants. The cowling tank designed around it was tight, closely fitting, with a fan behind the propeller to force cooling air into the cylinders at precisely the rate required. The frontal area was larger than a comparable inline engine installation, but the drag increase was smaller than expected, and the radial engine had an advantage that no inline engine could match. It could absorb battle damage, losing cylinders, taking debris, and continue running. Inline liquid-cooled engines, if their coolant lines were punctured, were dead within minutes. The FW-190A1 entered Luftwaffe service in the summer of 1941. The first combat reports from German pilots described an aircraft that could be flown aggressively in ways the Bf-109 could not. The Bf-109 had a narrow undercarriage. Its main wheels were set close together and angled inward, making landings on rough or short airstrips genuinely dangerous, and a significant proportion of Bf-109 losses throughout the war were ground accidents rather than combat kills. The FW-190 had a wide track undercarriage and was considered substantially easier to operate from forward airfields. It also had 4 20mm cannon and 2 13mm machine guns, a heavier armament than any Spitfire variant then in service. When RAF pilots finally encountered the FW-190 in numbers over the Channel in late 1941 and early 1942, the experience was uniform and severe. The Spitfire 5, the RAF's frontline fighter, was outperformed in every measurable category except turning circle. The FW-190 was 30 to 40 kilometers per hour, 18 to 25 miles per hour, faster in level flight at medium altitudes. It had a higher rate of roll, allowing it to reverse direction faster than the Spitfire pilot could follow. It could dive away without the engine cutting out, a consequence of the Spitfire's Merlin engine, which used a carburetor that starved the engine of fuel under negative G maneuvers. British pilots attacking an FW-190 that half-rolled and dove could not follow without their engine stopping momentarily, by which time the German pilot had gained hundreds of meters of separation. The FW-190's combat debut was not just a tactical surprise. It was an intelligence failure of the first order. RAF Fighter Command had no reliable information on the aircraft's existence until it began killing their pilots. On the 23rd of June 1942, the problem was resolved by accident. Oberleutnant Armin Faber of Jagdgeschwader II, disoriented after a combat over the Bristol Channel, became confused about his navigation and landed his FW-190A3 at RAF Pembrey in Wales, believing it to be a French airfield. He stepped out of the aircraft and was arrested by a British officer armed with a Very pistol. The intact FW-190 was pushed into a hangar, examined, and flown by British test pilots within days. The subsequent technical analysis confirmed what fighter pilots had been reporting. The aircraft was, in the summer of 1942, superior to any British fighter in service. The RAF's response was the Spitfire 9, introduced in the summer of 1942 with the more powerful Merlin 61 engine, which restored parity at medium altitudes. At altitude above approximately 6,000 meters, 19,685 feet, the supercharged Spitfire 9 pulled ahead. At low and medium altitudes, the contest remained even into 1943. The FW-190 was continuously developed throughout the war. The D-Series, fitted with a Junkers UMO 213 inline engine, was competitive with the best Allied fighters at high altitude in the final year of the war. In its various versions, 20,001 FW-190s were built between 1940 and 1945. Kurt Tank survived the war, moved to Argentina in 1947, and designed fighter aircraft for the Argentine Air Force. In 1956, he moved to India, where he worked on jet aircraft development. He died in Munich in 1983, at the age of 84. The aircraft he designed in Bremen in 1937 surprised a generation of pilots who had been told it could not exist. It did exist. It flew over the channel for 3 months before anyone who mattered believed the reports. And on the 23rd of June, 1942, a disoriented German pilot handed one to the British intact, and the surprise was finally over.